In this video, I want to talk about the principal unit normal vector and binormal vectors. This is for a curve in space where you have the curve given by a vector function. Okay. I want to remind you of when we were deriving a formula for the curvature, the one that involved r prime and r double prime. We wrote r prime as a product of a couple things and then took the derivative using the product rule, and we ended up with r double prime was equal to this sum. Notice this sum is a linear combination of t and t prime, both these two vectors. And what do I mean by linear combination? I mean multiply each by a scalar and then add them. Right? This relationship tells me that the three vectors, which is the second derivative, the unit tangent vector, and the derivative of the unit tangent vector, all lie in the same plane. Right? If one of them is a linear combination of the other two, then they're all in the same plane. So when I think about a vector function, right, so I think about a curve in space, the vector t is the unit tangent vector. It's pointing in the same direction as the curve is moving, right, as the particle moves along that curve. Now, there's a whole plane worth of vectors that are perpendicular to that unit tangent vector. And what I want to do is I want to pick out one of them that's really special. And the thing is, that one is in the direction of t prime, because t and t prime, that plane is the plane that also contains the acceleration vector. And I would want to also say that t prime is pointing in the direction of the acceleration vector. If this is my unit tangent vector and this is the acceleration vector, there is a vector perpendicular to this one that's pointing sort of towards the acceleration, and there's one that's pointing away from the acceleration. I want the one pointing towards it, and I claim that I know it's this one because this coefficient out front is a positive number. ds dt is the length of the velocity vector, sorry, the first derivative, and that is that's a positive number. So this is pointing towards the acceleration vector, and so I want to use it. But it's not necessarily a unit vector. So I want to get a unit vector that's perpendicular to the tangent vector, but it's pointing in the direction sort of the acceleration vector. Okay, so I do that by making the following definition. Given a vector function r of t, we define the principal unit normal vector as n of t, which is t prime divided by the length of t prime. So whatever t prime is there, just scale it by its length, by 1 over its length, and it will now be a unit vector. So now I have t, which is the unit tangent vector, so it's in the direction of motion, and n, which is perpendicular to the direction of motion, but it's also in the plane of the acceleration vector, the tangent vector and the acceleration vector. And so then lastly, we define another vector, which is called the binormal vector. And the binormal vector is the cross product of t and n. Notice that both of these are unit vectors, and notice that they're perpendicular to each other. And I know they're perpendicular to each other because n is in the same direction as t prime, and t prime is the derivative of a constant length vector function. T is always length 1, so its derivative is perpendicular to itself. So t and t prime are perpendicular, and so n and t are parallel. So t and t and n are perpendicular to each other. So I know that the length of b is the length of this times the length of that times the sine of the angle in between them. The angle in between them is pi over 2, and so the sine of pi over 2 is 1, and both of these are length 1, and so the b vector here, the binormal, is also length 1. So what we have is we have now a set of 3 vectors, all unit vectors, and I'll hold my fingers up here like this, and I think of it like this, that this one coming at you is the unit tangent vector. It's the one moving in the direction of the curve. This one over here is the binormal vector, and this one up here, sorry, this one is the normal vector, and this one is the binormal vector. Right? As you move along the curve, it's like a 3D coordinate system that moves with the curve. And I'll show you some animations here in a moment. Let's do a reasonably simple example. So here's one of my favorite vector functions, cos t sine t, right? This is a helix with a essentially circle in the xy direction, but z is increasing linearly with t. So as x and y are trying to draw a circle, z just keeps getting bigger and bigger, and you're drawing a helix. Now, take the derivative, minus sine t, cos t, 1. The length of that derivative vector is the sum of the squares of all the components here. Take the square root. So the square root of sine squared t plus cos squared t plus 1 squared, which is 1, and the sine squared t plus cosine squared t is 1, and you end up with the square root of 2. So take r prime divided by the length of r prime, then that would be the unit tangent vector. So the unit tangent vector is just divide each of those by radical 2. Now, I'm going to take the derivative of that with respect to t. So minus cos t over radical 2, minus sine t over radical 2, and 0, taking the derivative of each piece. Then take the length of that. So it's this squared plus that squared plus 0 squared, which is, factor out the half, and you get a 1 times a half, which is a half, and sum to the square root. It's the square root of a half, which is 1 over the square root of 2. So n is t prime divided by the length of t prime, which is this thing, all divided by 1 over the square root of 2. When you divide that in there, the square root of 2, the 1 over square root of 2's cancel out, and you just get minus cos t minus sine t, 0. So there's that. And then we have the binormal vector, which is the cross product of t with n. So this was t, that's n, and we do this, giving us the binormal vector is that. Okay. So this is interesting in that the binormal vector always has, in this case, always has a constant z value here. So as you're going around that helix, the binormal vector, well, because the helix heading uphill a little bit, you can tilt that whole thing back, right? As it's spinning around like this, that binormal vector is always pointing up the same amount. It's pointing in different directions with respect to x and y as you turn this way, but it's always got the same amount pointing up because that helix is always growing at that same amount. Okay. Let's take a quick look at some pictures here. So the first picture I have here is that helix that we just looked at, but it's not letting me do this. Here we go. The z component is squashed a little bit, so it doesn't rise quite so fast. But what I have drawn here is in red is the position vector pointing out to here. The blue is the unit tangent vector, and the purple is the unit normal vector. And if I just click and let this animate, you can see it'll go around, and the blue vector is always tangent, purple vector is always perpendicular to the curve. Here's another picture for you, animation. I got a little more complicated curve this time. Here's the vector function. Well, I'll show you down here. It's a trefoil knot. It's a single loop that ties a knot in itself. The vector function is here. Of course, the unit tangent vector is the derivative of the vector function divided by the length of the derivative. The normal vector then is the derivative of the tangent vector divided by the length of the unit tangent vector, and then the binormal is the cross product of t and n. Now, every time in this piece of software where you see this ... it means that there's some hidden calculations And so there's the calculations. When the vector function is not pretty simple, these get really big really fast. So there's the unit tangent vector. There's the calculations for the normal vector. They just go off the screen. They're huge. And the binormal, yeah, it's big. But that's all fine and dandy because it allows us to have this really cool picture here. So what you see here is the curve. Let's increase the density a little bit. And the black curve you can see is, as I move it around, it's easier to see what it looks like. It's a knot. It's called a trefoil knot. And I can see as well here this little red vector, which is the unit tangent vector. The blue one is the binormal vector, and the purple one is blue is normal, purple is binormal right up here. Red is tangent, and is normal is blue, binormal is purple. And when I click on this, you can see it move around. Actually, I'm lying to you. Those are not unit vectors. I stretched them to like 2 just to make them a little more visible. But you can see that the red one is always tangent, the blue one is the normal vector, and the purple one is the binormal vector. The red and the blue are essentially describing the plane that the curve is moving in instantaneously, and the purple one is perpendicular to that. There's something that goes on there through the middle where it looks like the whole frame spins. Yeah, that's a notion called torsion, which is in some Calc 3 books. It's not one we'll cover. It's essentially measured by the rate of change in the B vector. Right? So as it spins around there, the B vector is changing rather rapidly, and that's called torsion. So curvature and torsion are 2 numbers that are assigned to each point on the curve, which is intrinsic to the curve. Somehow there's an amount of curvature that's happening, and there's an amount of spin that's happening, amount of torsion that's happening. Right? Now, the thing I like about having these TNB vectors is that they create a coordinate system on the curve, right? Where t is parallel to the curve and n and b are perpendicular to the curve. And so in this picture over here, which you can't see because it's not drawing it, let me zoom out and zoom back in again, see if I can get it to draw what I want. Yes. What I'm doing here is that's this line right here, S. S equals r plus n cos theta plus b sine theta. I am using the n and the b vectors to draw a circle, right? And then I'm shifting it so that it's the center of the circle is on the curve. And this allows me to draw surfaces that are essentially tubes around space curves. So if you give me a curve, I can draw a tube around it because I can calculate n and b and use those vectors as a basis for a coordinate system to draw a circle in. Of course, I could change that circle to be other things as well. I could make it more elliptical. We could like throw a 2 in here and see what happens. That's not what I meant. Let's try that again. There we go. Yeah, so this is now more, it's longer in one direction than the other. The cross sections are now ellipses. Boy, that looks awful. So let's get rid of that. Yeah, and I can see the torsion happening here too, just because of the way I'm drawing it. That going through this stretch and this stretch and that stretch, there seems to be a twisting that happens. It seems that my video has frozen. I don't know if it actually has frozen or not, but it looks like it from my side. So anyway, there's some TNB frames, and at least one use for them.